So in this lecture, we're going to start talking about research that shows that Thorndike's theoretical law of effect really can't explain all types of instrumental learning. So let's just review really quickly. Thorndike's theoretical law of effect makes some assumptions. First, animals must behave in order to learn. We learn by doing. So there has to be behavior, and that behavior has to be followed by an appetitive S2. It has to be rewarded. So in order for an animal to learn, it has to behave, and it has to be rewarded for the associations between the S1 and the R1 to occur. Animals do not anticipate the consequences of their actions. We do not require mental representation of what's to come, anticipation. The S2 only serves the function of creating the association between the S1 and the R1. But some researchers at the time thought this was a bit too simplistic, or thought that it made animals seem like just automatons or robots, SR, 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 that govern all their behavior, and they don't think. According to Thorndike's theoretical law of effect, they don't anticipate. They don't have mental representation of things. Humans do. Why shouldn't animals, in some circumstances, anticipate, think about their consequences of their action? So this led to a very famous researcher, American psychologist named Edward Tolman. And Edward Tolman worked at Berkeley, and he's considered to be sort of the father of modern day cognitive psychology. Cognitive psychology is the study of memory and decision making and language and representation and even consciousness. And so he was one of the first to study behavioral genetics too. Not a lot of people know that about Tolman. They think of him as more of cognitive psychology, but behavioral genetics is a really big field now. And he was working on selective breeding in mice to see if selective breeding could make mice run faster through a maze. His field was called purposive behaviorism. Purposive behaviorism, meaning purpose of behaviorism. He was still considered a behaviorist in Thorndike and Pavlov and Hull and Skinner, but he started thinking this wasn't enough. That it's not just stimulus response or not just automatic behaviors, but there might be some thinking processes going on that we can't really see. And one of the first experiments that he did that kind of tried to demonstrate this was an experiment called latent learning. Latent means kind of hidden. So we have two groups. We have group one, and this group was running through a maze, group of rats running through a maze, and it was deprived at the time, meaning it was hungry. And when it got to the end of the maze, there was food, and that was rewarding, and everything makes sense, right? The animal learns to run through the maze more quickly, and receives the reward, and so therefore learns. Group two are well-fed rats that ran through the maze. In other words, they got to the end of the maze, they found food, but they didn't eat the food because they're not hungry. They were stuffed. They got plenty of food before even going into the maze. So while there was behavior going through the maze, running through the maze, there wasn't reward. So group two shouldn't learn. There shouldn't be series of SR associations created because the animal wasn't rewarded. But then they were tested hungry. They were both tested hungry, meaning that group two now has a motivation to get to the end. And the question is, when it was trained without reward, did it still learn without reward? Remember, group two is not rewarded for going through the maze because it's not hungry and the food isn't rewarding. So here's the result. This is the speed in seconds. And you can see group one, who is very hungry, starts off navigating the maze and gets faster and faster and faster over the course of training. Group two was not fed at the end of the maze because it wasn't hungry, but it learned that food was there. It just didn't eat it. And you can see it remained pretty slow. Got a little faster, but remained pretty slow. But in testing, both groups are hungry. Group 2 is hungry and almost instantly runs fast through the maze. Meaning that during this process here, when it was navigating the maze and not being rewarded, it did learn about the maze, it did learn how to navigate the maze, and it did learn that food was at the end, even though that food wasn't rewarding at this time. In other words, it learned without reward, because that was demonstrated as soon as it had a motivation to get the food, it ran extremely fast. This kind of goes against Thorndike's theoretical law effect that reward was necessary for learning the maze. The next experiment I kind of like. It's kind of interesting. It was also done in Berkeley in Tolman's lab by somebody named Elliot. And this is what happened. The animals learned to navigate a maze, right? They used Hampton Court mazes in that lab. And they measured errors, number of times the animal turned the wrong way, went down the wrong path. Okay, so group 1, for the first 10 trials, they were rewarded with bran mash. That's what they got at the end. Now, what is bran mash? Bran mash is the best tasting food for rats. Oh, it's delicious. It's got oats and it's got sugar and it's got honey. Oh, it's nuts. It's delicious. It's the favorite food. In the second 10 trials, they ran through the maze and were rewarded with sunflower seeds. Sunflower seeds? Well, if I'm a hungry rat, I'll eat it, but I gotta crack them open. It's not all tasty. It's only, okay, I'll eat it, but it's not very good. So they were switched from getting a very good reward to getting one that's edible, but not very good. The question is, did this group anticipate saying, oh, I know what I'm going to get. I'm going to get the really good reward, and then didn't get it? Group 2 started with sunflower seeds, was rewarded for going through the maze to get sunflower seeds. It was a hungry animal, and it ate the sunflower seeds, but then the next 10 trials, it gets to the end, and what's there? The best tasting rat food in the world. Honey and oats and deliciousness. So we're switching from extremely good to mediocre, and from mediocre to extremely good. So let's make some assumptions just by Thorndike's idea. The greater the value of the reinforcer, the greater the SR association. The better the S2, the stronger this connection. So group 1 started with the bran mash, should have really strong associations. Really strong, and group 2 should have associations but not as strong. Why? Group 1, the S2 was bran mash in the first 10 trials. Delicious, delicious, delicious. In group 2, the S2 was sunflower seeds. All right, well, I'll eat it, but whatever. Here's the results. Group 1 started with bran mash, and they got really fast. They did really well. Group 2 started with sunflower seeds, and they did okay. You know, sunflower seeds okay. So far, this is fitting with Thorndike's theoretical law of effect. Group 2's reward wasn't as valuable as Group 1, so Group 2 didn't learn as well and made more errors. But now we switch. Now, according to Thorndike's theoretical law of effect, Group 1 shouldn't anticipate getting the bran mash. It just should have strong associations. There is no expectation, according to Thorndike. But what happened was, as soon as on the 10th trial, it finds it gets the sunflower seeds, the next trials, it is just really bad behavior. Really slow. Tremendously low. Even though it learned and it'll eat the sunflower seeds, we get a really big disruption in behavior, and then slowly the animal gets a little bit better. You know, Elliot writes things like, these were friendly rats, and I like these rats, and then these rats were handleable, and you could bring them out of the cage, and they were cuddly and everything. And as soon as they came down and they found the sunflower seeds, what they did was they kind of urinated all over the maize. They didn't eat the sunflower seeds, and they bit me when I picked them up. Suddenly, this animal is one pissed off rat. This group here, sunflower seeds, okay, and then on the 10th trial, they get the bran mash. Oh my gosh. And we get this sudden increase in behavior that happens right after. Meaning, I expected to get this crappy food, and I got this great food, woohoo! And now I'll run down there, I won't make any errors. So this animal obviously learned really well, and it was able to demonstrate it once it had this high motivation. So in a strict Thorndikean assumption, the group in red here, the group 1 with the bran mash, should have kept going really fast. Because there was no anticipation, there was no expectation, and if anything, it should get a little slower to accommodate the associations created by sunflower seeds. But the fact that the animal wouldn't eat the sunflower seeds for several trials and got really mad and it made tons and tons of errors said, I think this animal really anticipated getting that delicious food, and when it didn't get it, it basically showed the rat version of a middle finger to the researchers. So we have two kinds of things happen here. One is called negative incentive contrast. Negative incentive. This is switching from a very high and valuable and reward to a lower reward produces a sudden decrease in performance. And we see this in humans all the time. Imagine somebody working at a job and they're making $50,000 a year and everything's fine. All of a sudden the company goes through a hard time and their salary is cut from $50,000 to $40,000 a year. That is a contrast. And you can see that follows that is some really disruptive behavior. As opposed to another group that normally got $30,000 a year for their job, suddenly they get $40,000. Their behavior just gets so much better, even though both groups are now getting $40,000. So switching from a low preferred reward to a high preferred reward, we get this sudden increase in accuracy, in effort, in behavior, and that's called positive incentive contrast. And we can use these kinds of tools and think about them in jobs. For example, giving somebody suddenly a bonus. Maybe you say, I want to pay my employees $50,000 a year. That's what I'm budgeting for. Is it best to just give them $50,000 a year? Or is it best to give them $40,000 a year and give them bonuses of $5,000 a couple times a year? Oh, I didn't expect that, and we're going to get better performance. Results indicate that animals anticipate reward. Now, this was done in another experiment at Berkeley in Tolman's lab by somebody named Crespi. And Crespi said, yes, the Elliott's experiment was great, but let's really do this right. Let's really be more accurate, and let's have some control groups. So we have a shuttle box or a running box, and the animal runs from one end to the other. We don't have all these moving around in mazes and taking lefts and rights and assessing errors. We just have running speed. Isn't that an easy thing to record? How long does it take the rat to get from one end to the other? So here's the rat, and in one group, the rat runs down and it gets a quantitative amount of food. Not quality, as in bran mash versus sunflower seeds, but quantitative versus like 6 niblets of food. That's good. Runs down, gets 6 niblets of food. And then, after many trials, it runs down and it gets 1. Now it got really fast. 6 niblets of food is great, it's hungry, and now it gets 1. And then what we find is after it goes from 6 to 1, the animal gets really slow. And in fact, it'll run kind of at the beginning, and then it'll get a little slower, and then it'll slower, and then it'll kind of go back and forth here, and then it won't eat the little one niblet of food, and it'll go back and forth. Even though it's the same niblet of food, it's just 1 instead of 6, you can see its disruptive behavior. So here's the experiment. Nice controlled experiment. Group 1 starts with 6 and moves to 1. Many trials of 6, and then now it only gets 1. That's negative contrast. And group 2 is just simply a control group. Well, what would happen to a group if it just kept getting 6? So now we can have a nice comparison here. Group 2 is a control for group 1. Group 3 is positive incentive contrast, meaning it goes from 1, no, okay, that's okay, I'm hungry, I only got 1, but whatever, to 6, woohoo, 6, that's fantastic. And we just have a control group. What happens to a group that always gets 1 after the switch? Switches from 1 to 1, doesn't really switch. Nice controlled experiment. Same as Elliot, just a more controlled experiment, and we can look at something as simple as running speed. So let's look at these results. Group 1, remember, got 6. And you can see in red, group 1 getting really fast. And then it is switched, and suddenly it gets really bad, immediately. This is one angry rat. And eventually we'll get down. Group 4 here always gets 1. So you can see what happens when this group gets 1 after getting 6. It gets much worse than the group that always got 1. Group 2 is the control group that always gets 6. And group 3 is positive incentive. That's in green here. And it gets a little better, and now suddenly is switched to 6. Woo, it gets better and actually overshoots. It actually gets better than group 2 that always got 6. Group 2 always gets 6, and that's about as fast as it's going to run. But what happens when you switch an animal from 1 to 6? It actually gets faster than any other group for a while. Gets elated. We might call that an elation effect. An elation effect because it went from 1, I expect 1, to 6, I got 6. Oh my gosh, that's fantastic. We call this group who went from 6 to 1, we can call that a depression effect, meaning that I expected 6 and I got 1 and I am pissed off and my performance is really disrupted. What these show is that in group 1 and in group 3, they anticipated the consequences of their action, and that is not Thorndike. The anticipation warrant does in fact affect behavior. Thorndike wasn't right there. It's not just what we call Thorndykean SR associations. There is something going on that goes beyond that. How do we explain it? Well, we need to think of parsimony again. The principle of parsimony, Morgan's canon. We can't just start adding human anthropomorphic thoughts and feelings. Let's think about if we can explain this using simple principles. So this is where we get into Amsel's theory of frustration. He wrote a whole book on it, Frustration Theory by Abram Amsel. Frustration is an innate emotional response to an unrealized anticipation of a reward. That's how Amsel defines it. So it's natural, born to, response to unrealized anticipation. It does have anticipation in there. I expect something, and it's not realized. I expected to get something, it's not realized. You've all experienced this. You thought you were going to go see a great movie, and it really kind of stunk. Or you thought you did great on an exam, and you got your score back, and it wasn't what you expected. You feel that emotion. You feel that emotional response. Frustration is a response. I feel frustration, right? I'm frustrated. It's an action. But with it is a sense of an emotion, a sense. So frustration is both a behavior, a response, but also can create a sensation, the sense of frustration. And frustration, like all kinds of stimuli, are conditionable. CSUS, Pavlovian conditionable. So here's what's happening. The animal anticipates the reward. So you have Thorndike, start box run, SR. I've come down there, I've gotten my 6 rewards, and that 6 reward create an association between S1 and R1. I'm in the start box, I run. Start box, run. And 6 is a very powerful reward, so it has a very strong SR association. We don't have to get rid of Thorndike. We don't say, oh, incentive contrast shows that Thorndike is completely irrelevant and doesn't apply to our behavior. No, Thorndike affects a lot of our behavior. What Elliott and Crespi and Tolman all tried to show was something else. Something else is affecting the behavior. There is a classical conditioning going on because 2 stimuli are occurring at the same time. The start box or the runway or all the stimuli associated in this runway and the reward. Classical conditioning, SS. This start box and this runway is associated with a 6 niblets of food. Animal runs down and now it finds only 1 niblet of food. Not what it anticipated. So now it's all angry. So now we create, through this process of this experience, we have 2 associations. We have start box and run. Start box, run. Thorndike's theoretical law of effect. Start box, run. Because that is a very strong association, because for many trials, I received this very high reward of 6 niblets of food. But now I'm creating another association, classical conditioning association. When I'm in this start box, when I'm running down the runway, these stimuli are associated with frustration. Because when I've been here before, the past few trials, I anticipated 6, I got 1, I felt frustrated. This area is a place of frustration. And in many ways, we simply have an R1, R2 incompatibility again. I can't run really fast and be really angry and frustrated at the same time. That frustration builds. This stimuli creates stronger associations. S1, start box, runway, whatever, run fast. R1, run fast. S2 is the delicious reward, the 6th reward, and that there's no problem. But when we switch it, and now the S2 is a small reward. Expected 6 got 1. The R2, the response to this is frustration. Unrealized anticipation of a reward creates frustration, and that frustration is conditionable. And now you have 2 things going on. I'm in this runway and I run quickly. I'm in this runway and I'm one pissed off rat. I'm frustrated. I feel it. These 2 are incompatible with each other, and the animal really slows down. Okay. So this is an interesting find. It shows that Thorndike isn't enough, that we need to add to it, that we need to look at these relationships of anticipation and classical conditioning. And researchers now wanted to figure out, well, do all animals anticipate? Do all animals show this frustration? And this is a field we've talked about before called comparative psychology. How do different species of animals behave and learn and have memory in the same situations? So we can look at honeybees, we can look at rats, we can look at pigeons, we can look at turtles, we can look at fish, and we can have them all do a type of incentive contrast experiment, see if they all do the same thing. Maybe only certain animals anticipate. Maybe that was an evolutionary change. So one of the most famous comparative psychologists is somebody named M.E. Bitterman, Mort Bitterman. And I worked for him. He was my PhD advisor at the University of Hawaii. He wrote hundreds and hundreds of papers, wrote books, and was a really world famous comparative psychologist. And in our lab, we studied honeybees and pigeons and different types of fish. And he had studied things like turtles and octopus and a bunch of different stuff. And he did an experiment with goldfish, a contrast experiment. And he did the same thing as Crespi did. He just, instead of having the fish run down, the fish swam. It was a filled runway, which was called a swimway, right? So first of all, you can't just stick a fish in there and have him run down because it doesn't have legs. So you have to fill it with water. That's an easy one. And get the animal hungry, and you give them these little worms, these tiny little worms that you can get at any pet store, and these fish really like these worms. And the fish swims down, and it chomps on the worms. Some groups got 20 worms, and some just got one worm when it got down there. Same experiment as Crespi, just with fish and with worms. So, group 1 got 20, hungry animal, got 20, delicious, and then was switched to 1. One group had 20 and continued to have 20, again a control group for 1. The other group was positive incentive contrast experimental design. It just got 1, and then it switched to 20. Yay, really great, I'm so hungry, 20's great. And then we have a control group. What does a fish do that always gets 1? Okay? And these are the results that Bitterman found. A group that was switched from 20 to 1 still maintained really high behavior. Did not show the sudden change and slowing that we see in the rats. It just kept running. It kept swimming really quickly. And it got a little slower, but it took many trials. The group that went from 20 to 20, it was pretty active. 20 to 1 and 20 to 20 kept pretty similar behavior for a long time. The other group went from 1, that's in green, to 20, and it didn't suddenly get really a lot faster. That elation effect we saw in the rats, it kind of just got a little slower and got a little better compared to the group that got 1 to 1, went from 1 to 1. So what does this say? Well, something's different in fish than in rats. Maybe fish don't anticipate. Maybe fish are strictly bound by Thorndike's theoretical law of effect, SR. Don't anticipate, don't think of the consequences. I'm just a fish, I'm just an SR, I'm just a little tiny fish robot. Maybe fish don't get frustrated. They don't have that innate emotional response to unrealized anticipation of a poor reward. But something is different here between fish and rats. And he theorized that somewhere here in the evolutionary tree that branched off to become fish and then branched off to become mammals and birds and stuff, something in this branch did not evolve to anticipate. And these animals did. They became higher. It's not common to find differences in learning between animals of different species. Remember, the general process approach says there are basic laws of learning that we can apply to most animals. So that was kind of a big find, this difference. All right, so let's end with this other experimental design that I kind of like. It's kind of fun because it's really looking at the difference between Thorndike and the ideas of Tolman, the ideas of anticipation. So let's look at the experiment and my wonderful animation. This is called irrelevant incentive. And there are many versions of irrelevant incentive experiments. This is called irrelevant incentive single drive experiment. Single drive meaning it has one drive at the beginning. It's hungry. It's not hungry and thirsty, and it just has one drive of hunger. It's got all the water it needs. So this is how we do it. We make the animal hungry, goes down, takes a right, and in a little T maze, and eats the food and is happy and is rewarded. Then we make sure, by putting a little barrier there, that it takes a left and it gets to the end and there's water there. It's not in a bottle, it's in a little dish, but it's not rewarded for that. Why? Because it's not thirsty. It's got plenty of water. In fact, it drinks water before it goes. So it is rewarded for going right and not rewarded for going left, but it does go left. And it does learn, and maybe, that there's water down there. We do this trial after trial, and we make sure that it goes down to the right an equal number of times to go down to the left. We can do that by forcing the animal's behavior. And then we change the drive. The animal was hungry in the first part of the experiment, and now we give them tons and tons of food, and maybe it's like some salty potato chips, and we deprive it from water, and now it's full of food, but it's really thirsty. We change the drive, and then we test. The animal's thirsty, and we're going to test the animal. Which way should it go? So let's make some predictions. According to Thorndike's theoretical law of effect, what was learned in the first part of the experiment? S, start box, take a right, R1, that's rewarded. Start box, S, R1, taking a left, was not rewarded. So the animal made an R1, S1, R1 connection of going to the right, not to the left. That was what was learned. According to Thorndike, where should the animal go when made thirsty and not hungry? Think about it. And according to Tolman, Tolman's about anticipation. Tolman's about a thinking animal. During here, even though it went to this side and didn't drink any water, Tolman would say, yeah, but learned water was over there. Learned that there's some water there. So now we have this nice experiment that kind of puts these two theories to the test against each other. Here's what happens. The animal was trained. He was hungry. He went to the right and got food. He went to the left and he didn't drink the water because he wasn't thirsty. Over and over and over again. Then we make the animal thirsty and not hungry, and we test them. Thorndike would predict the animal would go to the right and not eat the food because it's just stimulus response, not anticipation. And Tolman would say, yeah, but the animal knows water's over there and it's kind of thirsty. Here's what happens. Most of the animals, they go to the right. Even though it's thirsty, even though it doesn't eat the food, it's still that very strong SR association was created, and that's what it does. This supports Thorndike. The irrelevant incentive single drive experiment supports Thorndike's theoretical law of effect, and not Tolman. Tolman would say, the rat should know there's water over there. He's thirsty. He should go there. He doesn't go there. So let's do another experiment. This is called irrelevant incentive double drive. The animal's both hungry and thirsty. And again, goes to the right, gets some food. Is that rewarding to the animal? Yes, it's hungry. So we've made a start box, turn right association, S1, R1 association. And then, of course, we make sure the animal goes to the other side. Is it rewarded for going to the other side, for taking a left? Yes, it was thirsty. So there's an SR association to go to the right and an SR association to go to the left, and those should be equally strong because they were rewarded for both sides. They decreased a primary drive of hunger and thirst. Then we give the animal a bunch of salty potato chips or whatever, and we give it and make it so it only has one drive. It's only hungry, or in this case, it's only thirsty. I'm thirsty. Where should the animal go? Should it go to the food? Should it go to the water? Now, that depends on the theory. According to Thorndike, where should the animal go? Well, during training, it made an SR association going right and an SR association going left. So Thorndike really wouldn't make a prediction here. Thorndike would say it's a coin toss. There's SR associations for both directions, and so if we ran 20 animals, 10 should go to the left, 10 should go to the right. According to Thorndike, where should the animal go? Well, we don't make that prediction. According to Tolman, where should the animal go? It's thirsty now. Tolman would say the animal understands the consequences of its actions and should go over to the water. And what do we find when made thirsty in a double drive? If we ran 20 animals, 19 or so of them would go over to the water. They would mostly go to the water. So, if Thorndike's theoretical law of effect, SR associations, is not making a prediction here, is not telling the animal to go one way or the other, something else is happening. Something that's more in the line of theories of Tolman. The animal did know there was water over there, and when it doesn't have these SR associations, which are very strong, it can use that other information, the Tolman kind of information, to make its choices. So what this lecture shows us is, one, Thorndike's theoretical law of effect is very powerful. It's not wrong. It's just not complete. And Tolman said something else is going on here. And we start adding things like classical conditioning. We add things like anticipation. We add things like frustration.